First thing I wanted to tell you is that I'm not a cosmologist.
Sorry, can you speak closer to the podium?
Yeah. Can you hear me now? I'm not a cosmologist. That's what I was saying. Not a cosmologist. I'm in the wrong session. But thank you for bearing with me. I do this thing called near field cosmology. So that's kind of mock thing where you study high redshift physics by looking at nearby low mass stars. So you can actually do quite a bit. I will try to convince you that there is a very interesting application later on. But typically what I do, and this is basically my spot to explain to you what I do, so then you can maybe come and talk to me, because I'm here on a sabbatical visit until July from the Institute of Astronomy in Cambridge. I sit on the 5th floor. So typically I study the Milky Way, how it looks like today. There's still questions, open questions, but the most pressing question is why it looks like this today, and so how we've formed and evolved. And we use stars to trace, obviously, our galaxy. But what I'm also interested in is the stellar evolution. So there are some huge problems in stellar evolution and some unanswered questions, especially in evolution of multiple systems, where many exciting things can happen. I work on large data sets, typically examples, Sloan, Gaia, and looking forward to and kind of planning to get into the data provided by DESI, which is taking data now, and of course, coming right up with foremost. Interested in applications of machine learning to some of the problems that we've encountered with large data sets. And another thing that I'm very keen to discuss with you guys is the time domain, both to do with quasi-periodic behavior in, say, stars, and also transient phenomena that can be not limited to our galaxy and stars, and can be at cosmological redshifts. Since I work a lot with Gaia, so I wanted to give you some highlights on what Gaia has taught us about some of the things that I just described, the formation of the Milky Way, for example. You can use Gaia to detect tons of galactic halo substructure, and that's interesting because these are the kind of the remnants of the earliest formed dark matter subhalos, and if they were populated with stars, you can study them, reconstruct their properties, learn about early structure formation and probably dark matter. One example of measuring directly a mass of a galaxy has been carried out using the Gaia data and the Large Magellanic Cloud. And so here's my claim to you. I don't know if you find it surprising or not. This is probably the only measurement of a total mass of dark matter in single galaxy. So I'm claiming it's impossible typically to do in other circumstances. But here we have an example where a total mass, kind of the virial mass, can be probed directly, which I think is very interesting. So what Gaia taught us also is that the Milky Way was shaped by a single event that happened 10 giga-years ago, so around redshift 2. And what that means is that there could have been a whole spectrum of tidally induced transformation of the galaxy that it undergone as a result of this interaction, which kind of that just stayed there, right? So nothing else that important happened after all, right? So that opens a whole Pandora box of what happened to the Milky Way, how it transformed 10 giga-years ago. So that's a completely theoretical study. One thing we've learned by looking at this one single event is that massive satellites evolve their orbits in a completely unexpected fashion. So that's not recorded in the bibliography. So typically what's assumed for a massive body under dynamical friction, it will circularize its orbit as it sinks to the bottom of the potential well. What we see with massive satellites are typically involved in kind of major merger events is that satellites orbit can very efficiently radialize, so completely different behavior. And that's what we're studying at the moment. And there are some interesting implications for this. And then the last strand of what I'm doing currently is looking at unresolved stellar companions. So because they are direct probes of, for example, common envelope evolution, which is a theoretical thing that is invoked to make very close binary systems. So for example, sources of gravitational wave radiation, but is not directly observed. But with Guy, you can actually now study these very tight, completely unresolved stellar companions. And so if I have a minute, yeah, 30 seconds, the application of all of this together is taking this last major merger, right? And because it's phase mixing in the Milky Way for the last 10 years, a lot of its stars are now in the solar neighborhood. So you can see the stars right in front of your nose. It means that you can measure their spectra with an amazing signal to noise. So you can measure abundances of things like manganese and nickel very, very precisely. So because it's one galaxy, you can now model the evolution of these abundances as a function of some element ratio of, say, iron to hydrogen. And that gives you a yield of manganese and nickel. And so manganese and nickel typically produce in type 1a supernova explosions. So you can say what kind of explosion is needed to produce these yields. And so what it turns out is that we see a very clear evidence for sub-Chandrasekhar explosions. Not only that, we also see that there is a very strong evolution of the yield with metallicity. So this is it has direct implications for cosmological probes, right? Because there is irreducible scatter in magnitudes and luminosities of type 1a supernova of 0.15 mag. So perhaps some of it could be explained by looking at these sub-Chandra models, which we see evidence for. Sorry, thank you.
Thank you very much. We probably have time for a very quick question while Patrick comes up, if there is a quick question. Otherwise, I'm sure he'll be happy to field questions over coffee or lunch. Okay, if not, we'll move on to Patrick.
All right. All right, so today I'm going to talk about, hi, my name's Patrick. I'm a postdoc at NYU. I spend my time thinking about all things line intensity mapping, but today I'm going to highlight the first results from an experiment that I lead the science working group on called the carbon monoxide mapping array project. Intensity mapping in extremely brief, the idea is basically that detecting individual high redshift galaxies is hard, but if we're cosmologists, we don't necessarily care about individual objects so much as the population. So instead of trying to measure, individual galaxies as denoted by these dots on the left, where maybe we could only detect the 1% of the brightest ones, we make a low resolution map and of the aggregate emission from all of the galaxies, and then do statistics at that to learn about fundamental cosmology and galaxy evolution. The advantage is it basically allows you to cover large areas in principle more quickly and efficiently than you can if you have to actually find individual objects. COMAP is a project we started taking data in the summer of 2019 at the Owens Valley Radio Observatory in California with this lovely 10-meter dish here. The primary goal of our 5-year Pathfinder observation that's ongoing is to map carbon monoxide emission at redshift of about 3, so somewhere near the peak of star formation. Carbon monoxide is a tracer of star formation. It traces molecular gas, which stars are made out of. And so it traces a lot of very important properties of the high redshift interstellar medium. We have a lovely collaboration slide. We've got a 30-member collaboration. And this, about a month ago, we released our first season science results. So there's a lot of things going on in this plot that I could talk about for like next hour. But just to quickly explain the salient features, this yellow point is the only existing intensity mapping measurement in this redshift range and frequency range. These green points are basically the limit on the power spectrum that is allowed by those measurements. And the solid lines are individual theoretical models. This pink bar is our upper limit from our first year of data. And the kind of faded cyan region is what we expect from the 5-year of the Pathfinder. So salient features is we're an order of magnitude better. We've reduced the allowed space by an order of magnitude. And with our 1 year of data and with 5 years of data, we expect to be able to detect basically all of the models in the literature. So if we don't see anything after 5 years, something weird is going on, and we just figured that out. Science-wise, you can turn these power spectra The amplitude of these power spectra, glossing over a lot of detail, basically tells you the total amount of molecular gas in your survey. So you can turn these power spectra into a constraint on the cosmic molecular gas history. Here, the gray points are measurements from directly imaged galaxy surveys. The red boxes are from the existing intensity mapping measurements, which maybe are kind of systematically a little bit higher at these redshifts. A little bit too early to be certain, but is maybe interesting. And then the green arrow is our current upper limit, which is within about a factor of 2 of the existing models. And the 2 green boxes show the forecasted constraints after 5 years for kind of 2 representative of those models from the previous plot. And so, we will either be able to confirm that there's a little bit of an excess in the intensity mapping data, or we'll be able to basically make a measurement of comparable sensitivity to direct surveys, but measuring the total aggregate emission rather than only the handful of brightest objects. We've also recently secured partial funding for the next stage of the project to happen after that Pathfinder, which is really exciting. Our current observation, like I said, is targeting the CO 1 to 0 line at 115 gigahertz, but it also gets a higher frequency 230 gigahertz line in that frequency as well. It's completely subdominant because it's coming from like redshift 7 in our current data. But if we add an additional lower frequency measurement, we can map that same CO 1 to 0 line at high redshift, cross-correlate the two, and do the same kind of measurement at reionization where we understand, the molecular ISM of galaxies even less well. And so that's going to be really exciting going forward. So we put out in November 7 papers on the subject, which was a lot of fun getting those out. So if you are interested in hearing more, you can either take a picture of this slide or just search CO map on archive. Or if you wanted about this or anything intensity mapping related, come talk to me. I'm at NYU and I'm generally around here on Fridays.
Thank you very much. We have time for a question if someone has a question. Oh, yes, thanks.
So is your the improvement from year 1 to year 5, is that mainly volume or signal to noise or what?
So the improvement is primarily just signal to noise, just increased depth. It's also, it's not, this is not the square root of 5 here. Over this first year of observation, we've gotten dramatically better control of systematics. So the amount of data we are able to keep per hour on the sky has increased over the year. So it's that improvement plus just 4 more years of data.
Great. And can Kate come up next for the next talk?
Hi, everyone. Mike. My name is Kate Story-Fisher. I'm a PhD candidate at NYU, and I work with David Hogg as well as Jeremy Tinker, which is going to be the project I'm talking to you about today. So this is the Amulus project, and specifically I'm working on emulation of beyond standard clustering statistics. So the Amulus project is a collaboration with many of us that is working to go to smaller and smaller scales and span cosmology space to do improved cosmological inference with emulation. So the first step is to generate our high resolution n-body simulations that span a sparse space of cosmologies because these simulations are really expensive. And then we're able to populate these with many galaxy bias models. And then because we can't compare these directly to our data because they're too high dimensional, we compute summary statistics on this data. But because of the said expensiveness of the simulations, we can't just compute these summary statistics at any set of parameters to be able to compare it to our data. So what we do is we train an emulator, in this case using a Gaussian process, to learn the correlation between the parameters and the statistics that we get out. And then what we're able to do is use a standard MCMC to apply our trained Gaussian process and then measure the parameters given our real data. All right, so that's the overall approach. How does it work? So I've trained emulators for some of the standard statistics that we often use in cosmology. So on the left, I have the projected correlation function, and you can see the form of it. In the top panel here, you can see the fractional error of our emulator in the middle. and then that error compared to the sample variance on the bottom plot. And I'm showing the same thing in the middle for the monopole of the correlation function and the quadrupole as well. And you can see that we do quite well in terms of accuracy. It can predict the 2-point statistics, the correlation function and the monopole to 1 to 5% accuracy, depending on the scale. The quadrupole not quite as well, but it still gives us important information. So then what I do with this particular project is go beyond these standard clustering statistics. And so I've picked a couple that are shown in literature to break some degeneracies in our cosmological parameters that we care about. So the underdensity probability function you can think of as throwing a bunch of randomly placed spheres into our catalog and counting up which ones have a number density less than some threshold. And so that's going to give us a measurement of kind of the void distribution. And then we also have the marked correlation function where I weight the galaxy pairs by the local density around each galaxy. And that's going to give us kind of something related to the monopole, but that has some dependence on the environment. And that's something we're really interested in because we are curious about this phenomenon of assembly bias, which is whether the masses of galaxies and halos and the number of galaxies and halos depends on something other than the halo mass. Okay, so how does this all work? So we can do this MCMC and get out our cosmological parameters for one of our test simulations here. So I know the truth that's in the dotted line. On the left, I have 3 of our important cosmological parameters, the matter density, sigma 8, and this gamma f, which measures deviations from GR. And on the right, I have a few of the galaxy bias parameters, the mass cutoff of satellites, the velocity bias of satellite galaxies, and also fn, which is one of our assembly bias parameters. So you can see that just using the projected correlation function does okay. It gives us some results better than the prior. This is what's often used in some of these big results we see. And then we add in the monopole and the quadrupole, and we get somewhat better constraints, particularly on the velocity bias of satellites, interestingly. And then when I add in my emulators for the underdensity probability function and the marked correlation function, I do a lot better in some of these recovery tests. So I snap on to the to more accurate recovery of especially sigma 8 you can see there, as well as gamma f, and I also recover them much more precisely. So I can do this for a large suite of recovery tests. I use 70 in my test. That's 7 cosmologies with 10 different HODs. And then the punchline is that including these statistics increases our constraining power on sigma 8 and omega m by 25%, and on our growth of structure parameter by 15%. And so these are really important increases for the level we're working with in precision cosmology. My secondary punchline is that we also see a good improvement in constraining assembly bias, which will be really important for constraining the galaxy halo connection, or understanding it, I should say. All right, so that was just one of the things I'm working on. I'm also interested in a lot of things, including most recently symmetry preserving machine learning for working with simulations, as well as maybe detecting gradients in large scale structure. So if you're curious about any of these things, feel free to get in touch. I'm also around here on Fridays. Thank you.
Thank you very much for that great talk. We have time for a quick question or two. Yes.
Okay, could you say something about your 10 HODs that you mentioned you're using? What do you mean by that? There's 10 different.
Yes. So we have a large range of HODs that we populate our simulations with, and then for the test simulations for each cosmology, we choose 10 unique HODs to try to span a range of space to see how we're recovering it for a range of HOD parameters. But in the end, we marginalize over the HODs to get our cosmology results.
Forms or
you
vary. How are they different?
They're the same functional form, 11-dimensional HOD, just varying the parameters within each one, as well as 3 assembly bias parameters.
Great, thank you very much. Can we have our next speaker Suror, who I think, yeah, great, thanks.
Hi, everyone. My name is Surur Sehergandhi, and I'm a graduate student at NYU. And today I'm going to talk about my work with Professor Yassin Ali Hamoud on solving the Boltzmann equation for dark matter and baryon scattering. So just to start off, I'm going to name a few of the probes which constrain this type of scattering. At the highest redshift, we have spectral distortions. Then there's the CMB anisotropies, 21 centimeter brightness temperature, Lyman alpha forest, and one of the most recent ones that has been used is the distribution of Milky Way satellites. And all of these probes are searching for a signal for this kind of scattering. And the CMB in particular is extremely high precision data, which is used to place bounds on the scattering cross section. And so in the presence of such high quality data, the accuracy of our methods for placing these bounds becomes all the more important. All of these methods currently are derive their bounds based on a very critical assumption. And that is that they assume that the velocity distribution of dark matter is Maxwell-Boltzmann. Now, this assumption is a simplifying assumption. It's not necessarily true in all cases, but it's great because it helps us actually calculate things. The heating rate and the momentum exchange rate has an analytical form if we make this assumption, and then we also don't need to worry about solving the full Boltzmann operator. But having a Maxwell-Boltzmann distribution means that the distribution is thermalized and interactions are efficient. However, if after decoupling with baryons, dark matter doesn't interact with itself efficiently, then F is going to deviate from Maxwell-Boltzmann, and it will no longer remain thermalized. So my goal is to check the validity of the Maxwell-Boltzmann assumption by exactly solving for the evolution of F in an isotropic and homogeneous universe, but not making any other assumptions about its form. So what we do is we get analytical expressions for the scattering rate, gamma, in one dimension. And we do this for models where the cross-section is proportional to the relative velocity v chi b raised to a power n, and n can have different values for different models. Now, in general, in 3 dimensions, this gamma has a highly non-trivial form, and it's definitely not analytical. But even in 1D, this is the first time we have exact expressions for gamma. And this gamma is a critical element that goes into solving the Boltzmann equation. And then we output the exact heating rate, Q chi dot, and then compare it with the Maxwell-Boltzmann heating rate, which is Q chi dot MB. So here in these plots, I'm showing, maybe I can use this. I'm showing different models, so different values of n, and the different colored curves. So the different panels are different models with different values of n. The different colored curves are different mass ratios between dark matter and baryons. And on the y-axis, I'm showing the fractional difference between the exact implementation and the Maxwell-Boltzmann solution. So you can see that, for example, in the top panel, the difference isn't that large. But in the bottom panel, the differences can get up to order 1. Now, what is interesting is that this is very similar to results that come from using the Fokker-Planck approximation to the Boltzmann collision operator. And this was done in 2019 by Yasin. And this shows that both of these methods have order 1 differences from Maxwell-Boltzmann in some cases. So this is reassuring because that means that the Maxwell-Boltzmann method that has been used so far isn't wildly wrong. And also, if we want higher accuracy, we have an approximation method which can be used, which is easier to implement in CMB codes. And it's closer to the exact solution, at least in this simplified 1-dimensional form. And that's all. Thank you.
Thanks very much. Do we have any questions? Colin?
Yeah, this is interesting. Just to get some physical intuition for what's going on, is it basically just that the baryon dark matter scattering is a small enough change to the original Maxwell-Boltzmann distribution that that assumption wasn't completely wrong beforehand? Because the physical reason that you gave, that the chi-chi scattering is inefficient at late times, would seem to suggest this could have been a significant effect.
Yeah, I think Maxwell-Boltzmann seems to work because around decoupling, like where these are peaking, is where dark matter is decoupling from baryons. So the difference is highest at those times. But once you go on to later times, the distribution of dark matter becomes narrow enough because the temperature has fallen far below the baryon temperature. And so the details of the distribution stop mattering. And because it's so narrow, you can just take the temperature and go with it, like in Maxwell-Boltzmann.
Okay, thanks.
Great, thank you. And our next speaker is.
Thank you.
Yeah, the top one is the pointer. And that goes forward.
All right. Hi, everybody. My name is Colin Hill. I'm a faculty member at Columbia and an ARS here at CCA. I wanted to give you a quick rundown of a few of the different things that we're doing in the cosmology group at Columbia. And of course, many of this also intersects work that's ongoing here. So just a quick run through who else in the group. So there's me up here. Maybe this isn't working. Boris, who's a postdoc in the group. Oh, there we go. Maybe there is. There we go. Cool. Boris, who's here also in the room. And then 3 grad students, Ola Kuziak and Alina Sabir, who you'll hear from later, and then also Kristen Sarau. And of course, there's a number of other folks at Columbia also working related topics. Some of whose work I'll show in a minute later. So the main goals of our group are to use the cosmic microwave background and other cosmological data to search for signals in new physics, and I'll talk about some of that shortly. To use the CMB as a backlight to probe cosmic structure formation at lower redshifts, and then also to develop multi-frequency component separation tools that enable this type of science. And a lot of what we're doing is motivated by the great data that we have from the Atacama Cosmology Telescope, shown here, as well as the Simons Observatory, which is being built at the same site, both of which are projects that we are heavily involved in. Okay, so first let me talk about extragalactic astrophysics. This is what I like to call cosmic microwave backlight, where we use the CMB to probe structure at lower redshifts, most prominently through the thermal Sunyaev-Zel'dovich effect, which probes the ionized gas pressure, and the kinematic Sunyaev-Zel'dovich effect, which probes the ionized gas density. And Ola will tell you more details about these in a few minutes. So this is kind of a summary plot of the range of halo mass and redshift that you can probe the gas properties in with these probes from a science white paper that Nick Botelli and I wrote for the Astro 2020 Decadal Survey. And you can see that, you know, lets us get out to higher redshifts and also lower masses than X-rays, for example. And in general, there's nice complementarity amongst these different probes that we have. So Nick and I are really excited to see that indeed our white paper had a big impact and was called out multiple places in the Decadal Survey report. No need to read all this text, but yeah, that was kind of a thrill for us. So here's one example of the type of thing that we're doing. So I've worked a lot in the last several years on what's called this projected field kinematic Ksd estimator, which Ola will tell you more about. We've now detected this a couple of times, reaching over 5 sigma now with Planck and Unwise data, and we expect that to improve substantially with ACT data soon. So what we've been developing recently is a halo model tool to calculate this signal theoretically. So Boris has written some beautiful code to do this, which lets us then interpret the measurements in terms of gas density profiles predicted by galaxy formation simulations. You run your hydro simulation, you get some prediction for how the gas is distributed around galaxies, and then you can compare that to these measurements. And this is a real forecast with real error bars predicted for cross correlation of existing ACT data that we have on disk with unwise galaxies. These are infrared selected galaxies around, say, redshift 1. And there's 3 different gas physics models shown here: an NFW profile for the gas, which we basically know is already ruled out, a purely adiabatic gas physics model, and then a model with significant AGN feedback. And these are drawn from Nick's hydro simulations. And you can see that we can distinguish these models at high significance. And really, we have enough signal to noise to even start to probe the details of the feedback mechanism through its impact on the gas. So I'm very excited about this, and I think that this field is going to be transformative in the next few years with the great data that we have. All right, now turning briefly to talk about new physics with the CMB. I've been interested the last few years with in detail in this H0 problem, which of course we heard about yesterday with the shoes team's latest update. It boils down to a simple question in terms of the cosmological physics involved. How can we increase the value of H0 inferred from CMB and large-scale structure data? I think the most promising approach that many of us have narrowed in on is to modify the dynamics in the pre-recombination universe in some fashion. So I've worked a lot on this model called early dark energy, where you introduce some new component that comprises about 10% of the cosmic energy budget at redshifts of order a few thousand. This FEDE is the fraction of the total cosmic energy budget that this stuff comprises. And you tune the potential of this scalar field that drives this in such a way that it rapidly vanishes and doesn't cause problems later in the history of the universe. What we found just a couple months ago with ACT-DR4 data was that there's actually a mild preference that's seen for this really dark energy. Let's say formally we said that it doesn't rule the model out, but it's preferred at roughly 2 or 3 sigma significance. And so that's captured in these posteriors on H0, where the solid curves here are lambda CDM fit to these data sets. The dash curve is this EDE model fit to the same data sets indicated in these colors. So Planck doesn't really prefer this EDE, so you get very little change if you look at Planck alone. Whereas ACT, if you compare any of these other solid to dashed curves, you can see that we get a significant increase in H0, which is coming from the fact that there's this mild preference for some of this early dark energy in the ACT data. So these hints were mild in DR4. We have much more precise data on disk from ACT already that will come out in about a year. And I'm very excited to see what we might find. There is one problem with many of these models. This is my last slide, which is that they often worsen the CMB large-scale structure S8 tension. And the physics for this is simple. It's related to the additional early ISW effect that's generated, for example, in this EDE scenario, which has to be compensated. So one way to get around this that we've come up with recently with Wayne Hu, Evan McDonough, and others is to introduce a coupling between the EDE field and the dark matter in a new model that we're calling the early dark sector. So this is the evolution of the EDE field on its potential. It starts out frozen and then rolls down and oscillates around the minimum. In this model we've constructed, the dark matter mass evolves in a fashion driven by this evolution, where it, in this case, increases from its value in the early universe to the late universe by about 0.5%. And I won't go into the changes here in detail in the posteriors, but we did find that this model is moderately promising in terms of reconciling this simultaneous S8 and H0 tension. So stay tuned, and thanks.
Thank you very much. I think unfortunately we probably have to move on, but I'm sure Colin will happily answer questions over lunch. So we'll move on to Shirley now.
Hello, everyone. Okay, let me try to do this quickly. I'm Shirley Ho. I'm a group leader at Cosmology Cross Data Science at CCA. I'm kind of doing this like for fun so that people can know me a little bit better. Stuff I do science-wise, I do statistical analysis, observe cosmological data sets, deep learning applications on all kinds of stuff, ponder secrets of the universe, learn new methods a lot. These days, just learning a lot. Stuff I do non-science-wise, I figure I would meet people like here as person. So I read and learn a lot about public policy, cross science, and geopolitics these days. I'm also really good at organizing parties in general. That caused my Airbnb account to be suspended. Stuff I'm usually most excited about recently is to accelerate simulations with deep learning methods from the vanilla stuff that we talked about, like UNet, to more recent transformers, which are natural language processing, natural language models. Also simulation-based inference on these Sloan Boss data sets. And I think a bunch of people here know about this and how much more information we can get from there. And more recently, we're just covering masses of moons and planets from real orbital data from NASA horizons with only deep learning and no physics. So I'm going to show you a couple movies for the things I'm most excited about recently. I changed a lot of what I usually do. So these 3 things, one is exciting simulations with deep learning. The other one is simulation-based inference, and we're discovering masses of moons and planets from real data without knowing any like Newton's law. So accelerating simulations with deep learning This is work actually led by Kimberly Stachenfeld, who is a DeepMind research scientist. Elaine Coy, who's a master student at CDS, actually working with us for a whole year and was a research associate, I forgot the exact title, at Flatiron. Miles Kramer and Drummond Fielding. Miles being student at Princeton who works a lot here, and Drummond Fielding who's a Flatiron fellow here, and a bunch of people at DeepMind. All this credit was actually not loaded because I added them quite late last night. Here's a movie I'm actually about to show, if I can click it to happen. On the top line is the ground truth, the middle is the predicted. On the cross here is density, the velocity in x by the pressure. I'm trying to find the right. Okay. And the pressure, and here's the spectral amplitude as a function of scale. This is actually really hard to use, it turns out. And if I can start this, I don't know if I can start this movie. Yes. So our prediction is actually doing quite well, I would say. This is using deep learning neural network. It is called dilated residual neural net. It's a little bit different from what we usually use for image recognition. Let me play that again. And we were able to make the machine learn it from a bunch of pre-trained data sets, bunch of data set that we actually ran. Drummond helped us a lot with this. And then it learned to predict the one next step. And then we take that output and we input it again and run it next step again and keep running it. And it's showing it about a row of about 160 steps. So if there's any errors, it blows up, right, in principle. So the fact that it doesn't blow up too much is actually quite good. Let me just show that again. And you can see that for the Fourier amplitude here, the spectral amplitude as a function of frequency, the two lines, one is the ground truth, the other one's predicted, actually rolls out pretty well all the way. So I thought that was pretty cool. And that's for turbulence simulation run by Athena++ for those who do turbulence simulation. The next one, I actually won't have time to talk about the other parts, which is to do simulation, deep learning accelerated simulation-based inference with BOS data, which I hope some of the people will talk about here. But I will talk about a little bit cool movie here, where we rediscover the mass of the moons and planets from real orbital data that we took from NASA Horizon telescope, Horizon satellite, and that for 30 years, we took that data set, throw it into a graph neural network, and in this graph neural network, learn how to predict the next time step. And it made these nice predictions. And it took a chunk out of this neural network, which is this graph neural network. This work led by Miles Kramer, Pablo Lemos, now Jeffrey, and Peter Battaglia, who's at DeepMind. And then you take that chunk out of the deep network and then interpret it using a large search tree of the equations. We recovered the Newton's law. Yes, we did not find GR, which is much harder. And then we recovered the masses of 31 planets and moons orbits. And what I'm going to show you is a movie of what happens of the inner solar system of the 3 years that we did not use for training data set. And for the inner solar system, compare the truth, which is the sort of semi-transparent one, a lighter one, and the solid one. Let me just show you here. So the sun is in the middle. You'll see slowly that you'll see a little bit of difference at the very end of the 3-year trainings, 3-year test sets. Yes, you don't see very much difference in error bar. But at the very end, there's a tiny bit. But basically, we do recover the planetary trajectories, the masses, and all that extremely well. And I think that's it. Thank you.
Great, thank you very much. We have time for one quick question. Yes.
You want to click the, sorry.
Yeah, your turbulence simulation was amazing, that agreement. But I wonder, would the machine learning model perform as well if, for example, you like tweak the viscosity of the fluid or something like that? Or do you have to keep it very constrained for it to work that well?
So it worked across like multiple different types of turbulence data. So this is just one that I show you. We have like 5 other ones that actually works. There's some actually follow-up work there that was actually doing. Remember how we interpret and find Newton's law for the next one that I showed you with the movie? We want to interpret and find the equations of these turbulence simulations and possibly other terms that we don't know about. And when we try to recover those equations, for certain simulations that have certain viscosity or certain, like, is it compressible, incompressible, they do better versus not as well. So depending on the conditions of the simulations, you might actually do better or less well.
Thank you.
Thank you. Very good question.
Thanks. Can we have our next speaker, Alexandra?
Hi everyone. My name is Ola Kusiak. I'm currently a third-year graduate student at Columbia University, working with Colin and Boris, and I'll be talking about probing the ionized gas thermodynamics in unwise galaxies with the Sunyaev-Zeldovich effect. So just a reminder for everyone, the Sunyaev-Zeldovich effect is the Doppler boost of the cosmic microwave background photons, inverse scattering of free electrons, and there are two types, thermal and kinematic, Ksd and Tse. In the thermal one, electrons have high temperatures due to the depth of gravitational well they are in, and the signal scales as electron pressure. Therefore, it traces only the dense structures in the universe, like galaxy clusters. And in the kinematic case, electrons have non-zero line of sight velocity, and the signal scales as electron momentum or mass density. And it can be used to trace the distribution of baryons. So it was used to, for instance, find the so-called missing baryons in the universe. So let's start with the Ksd. So we detected the Ksd signal with so-called projected field estimator. And the basic idea of this estimator is that the Ksd signal is already present in the CMB maps. And since the signal traces the overall mass distribution, it can be detected by cross-correlating it with any large-scale structure field, for instance, a galaxy over density map. However, the simple cross-correlation of Ksd and large-scale structure would vanish because of electrons' velocities, which are as likely to be positive as they are to be negative. Therefore, we square the CMB map first and then cross-correlate with large-scale structure. And also what is crucial about this estimator is that there is no redshift information needed for individual objects, just the general redshift distribution of the sample. And as I said, with the projected field test, with the Ksd measurement, we can constrain the baryon abundance. So we applied this estimator to data last year to the Unwise Galaxy Catalogue, which was made by our collaborator, Alex Królewski, and is based on the NASA mission. Unwise consists of 3 subsamples, blue, green, and red, of mean redshifts 0.6, 1.1, and 1.5, and it has over 500 million galaxies on the full sky. And you can see the general redshift distribution of each of the subsamples. But as I said, we don't need the redshifts for individual galaxies. And from the CMB side, we use the LGMCA map, which is based on Planck and W map, and also the Planck-Smika map. So here is the measurement for Ksd for Unwise. I'm showing only the 2 subsamples, 2 Unwise subsamples, blue and green here. And this is overall, this Ksd detection has 5.5 sigma signal to noise, and is the highest redshift Ksd measurement to date for the red sample. We introduced many new aspects of the analysis and modeling of this estimator. For instance, we introduced the magnification bias contributions, which is not negligible for such a high redshift samples. We use the asymmetric quadratic estimator to increase the signal to noise. We also introduced a new cleaning method, multiple dependent cleaning method, and extensively tested for foreground contamination, and also validated the results with different maps combinations. And as I advertised before, the baryon abundance can be constrained. So here are the numbers for each of the Unwise subsamples. And also, when you stare a little bit at the plots, you can see that the amplitude of the green sample is a little high, the AKSZ. The fiducial value is around 1. So we're trying to reinterpret the measurement in the Halo model regime, and Boris has been working on that. So also recently, I've been working on a complementary TSZ measurement for Unwise, this time with ACT, not with Planck. But as I mentioned, from now on, we want to do everything in the Halo model regime. So first, we need to constrain the Halo occupation distribution of these Unwise galaxies. So we'll be doing this with galaxy, and galaxy lensing data that we have from our collaborator, and they are shown on the plots. And these curves, the modeling they have been produced with Boris's code class SZ. And once we have the HOD parameters constrained for the Unwise galaxies, we can turn back to the TSZ measurement, or YG in this case. And here is a preliminary measurement of the TSZ for Unwise for the BOSS and D56 ACT regions. And with this measurement, we can, the goal of this measurement would be to constrain the electron pressure profile of the Unwise galaxies. So just to put everything together, we'll have the KSZ measurement. It will scale as number density TSZ, which would be proportional to electron pressure. And we can also add the lensing measurement, which will scale as the lensing measurement scales as the total integrated mass. So with this information, we can constrain the thermodynamic profile of gas associated with Unwise galaxies, and then further use it to get more information about the feedback events in these galaxies. And also, I've been working on a similar analysis for DS and ACT.
Thank you very much. Unfortunately, we have to move on, but I'm sure you'd be happy to take questions afterwards. Could we have our next speaker, Hongwan Liu, come up, please?
Hi everyone, my name is Hongwan Liu. I'm a postdoc at NYU and Princeton. I only have one slide, and I'm not going to go into anything specific. Just give you a spiel about why, someone like me who's interested in particle physics beyond the standard model, why looking at cosmological probes is extremely interesting, and tell you maybe along the way some of the interesting things that I've been thinking about on this slide here. So I would say, let's start with maybe a sample of the kind of exotic processes that may come from particle physics beyond the standard model that I'm really interested in. So taking, for example, the case of just dark matter, what are the kinds of new physics that you could have beyond the lambda CDM paradigm that you could hopefully look for signatures for in cosmology? So we would be interested in things like annihilation, where two dark matter particles meet each other and turn into two standard model particles. Dark matter can decay if it is unstable on cosmological timescales. It could scatter with the standard model, which is something that Suru already discussed a little bit about. And one last thing is that it could oscillate. Standard model and dark matter particles could oscillate, into each other, and that would leave interesting signatures in cosmology. So the main reason why I find cosmology such an interesting way to look for new physics signatures is because
the early universe is actually really relatively simple compared to some of the stuff that you might have to deal with all the way at the end of this redshift axis that I'm showing you here. So you don't have to do in terms of like the traditional way of looking for annihilation using for example indirect detection methods, you have to deal with like astrophysical backgrounds and so on. Whereas the early universe is generally simpler, it's very smooth. And also, especially after recombination, it's very cold. And so every time you get some kind of energy transfer between some unknown sector to the standard model sector, you can actually hope to pick up small energy injections. And the last thing, of course, is that you have a really long time to integrate stuff over, right? You have like 10 billion years for signals to build up and for you to detect it all the way at the far end of this axis. And so for all of these reasons, cosmological probes of dark matter processes tend to be very promising and very competitive compared with some of the other ways to look for these exotic processes. So let me just run down all of the stuff that I'm interested in, starting from way early in Redshift near the Big Bang, all the way down to today. So right at the beginning, like the one thing that we know from cosmological measurements is that we know what the dark matter abundance is. And so when we build particle physics models to try to figure out what dark matter is, that is the one key piece of data that we have, right? So one of the most interesting motivators for particle physics models of dark matter is to figure out how to actually produce dark matter at the correct abundance. And this is something that people have talked about, this simple scenario where you produce it via annihilations of two dark matter particles into standard model particles for many, many years. But for various reasons, we have become interested in a wide variety of other production mechanisms, and I'm really interested in a bunch of them. Then later on, as you come down to a redshift of like 10 to the 10, when the temperature of the universe was like an MeV or so, you could have dark matter processes like annihilation or decay messing around with what's happening during Big Bang nucleosynthesis or BBN. So around the time when you're producing all of the light elements that we see today, such as deuterium or helium, if you have anomalous energy injections coming from dark matter processes, for example, you're going to mess with abundances that you get at the end. And so BBN is actually a very powerful constraint on dark sector processes. Coming down even further, where recombination is, this is something that's very familiar with many people here at the CCA. Recombination produces, of course, the cosmic microwave background. And there are two things that I'm particularly interested in. One is the anisotropy power spectrum, where things like annihilation or decay can actually leave imprints on the power spectrum. And one of the things that I've been working on recently is that actually these calculations of how annihilation or decay leave their imprints on this power spectrum hasn't been done terribly accurately, and we want to see what happens when you put in all of the bells and whistles to get this calculation correct, and just to make sure that we haven't missed out any interesting effects when we set constraints on these kinds of processes with the power spectrum. The other thing that we're interested in is the spectral distortions to the CMB spectrum that can come from oscillations, for example, of photons into other like dark sector particles, such as axions or dark photons. And then further still, this 21 cm global signal and power spectrum is a very powerful probe of temperature of the intergalactic medium at a redshift of about 10 to 20. And again, dark sector processes such as scattering can cool the gas anomalously, and you would see these signatures in the global signal. And already there are some claims that maybe we might have seen such signatures. And I'm interested, and I have built some particle physics models to explain these kinds of anomalous coolings. And then all the way down, maybe to between a redshift of 2 and 5, we have measurements of the Lyman alpha forest, which again gives you a measurement of the IgM temperature at around those times. And again, these measurements are effective at constraining annihilation or decay, or even looking for additional exotic injection signatures at late redshifts. So I think I'll just leave it there for now. If you're interested in any of these topics, please come look for me on the 6th floor. I'm generally seated at the far end of the 6th floor on Thursdays and Fridays. Thank you.
Great. Thank you very much. We have time for one quick question, if there's a question. Otherwise, we can move on to Alina's talk. Thank you very much.
Hi, everyone. I'm Alina, a second year grad student at Columbia, and today I'll be talking about a project that I've been working on with Colin Hill and Boris Bollier. So as you can tell from the title of the slide, the goal of this project is to calculate an analog to the Ksd effect in the cosmic infrared background. So in the earlier talks, people have went over the Ksd effect, but I'll just go over it again just in case here as well. So the thermal Snaib-Zeldovich effect refers to a spectral distortion in the CMB, which results from the upscattering of the CMB photons on the hot electron gas that is present in our universe in places such as clusters of galaxies. So in the case of the CMB, we start off with this perfect blackbody spectrum. So here, just as an illustration, I include this beautiful plot from the preliminary results of the COBE space mission back in 1990, which shows just how precisely the CMB follows the blackbody spectrum shape. But then as the CMB photons travel to us from the surface of the last scattering, they encounter these energetic free electrons in the intercluster medium and undergo inverse Compton scattering, which means that they gain energy off of these electrons. So the actual spectrum that we observe has a small distortion. And here I included a plot from the early Snaib and Zeldovich papers, which shows the distorted spectrum. Now, ever since this derivation back in 1970, the Ksd effect has shown to be a very powerful probe of both cosmology and astrophysics. So more recently, for example, ACT has published a catalog of more than 4,000 clusters that were found using the Ksd, and also others have used a combination of galaxy data and CMB data to further study astrophysical processes such as feedback, because the Ksd effect allows us to further understand the physics of the ICM and CGM. But now the cosmic microwave background is not the only background light that we observe in the sky. We actually also observe a radio background and an infrared background, and we expect that those would also undergo the same physical process of inverse Compton scattering off of the hot electron gas. So in our project, we're concerned with the infrared, but earlier, a couple months ago, others have calculated the signal for the radio signal. So this CIB, the cosmic infrared background, is the radiation from the star-forming galaxies, which contain dust that absorbs some of the UV light from the stars and re-emits it in the infrared. So because the CIB sort of traces these star-forming galaxies, it can be modeled using a halo model formalism, which associates these star-forming galaxies with the dark matter halos. So in our project, we compute our CAB spectra using the class SD code, which is written by Boris, and we use the model for the CAB from McCarthy and Madhava-Charil 2021, which in turn relies on this other paper by Sheng in 2012, which for the first time proposed this halo model prescription for the CAB. So what you see here in the plot on the left is the CAB for the different minimum redshifts. So the darkest line here corresponds to the CAB emission as seen at redshift of 0, so integrated from the redshift of infinity to 0. So then what we do is we take our numerical CAB model and we apply the same inverse Compton scattering process to it. We integrate through the universe, taking into account the redshift evolution of both our CAB and also the sources responsible for the inverse Compton scattering. And we arrive at our newly calculated distortion in the plot on the right. So what you see in this plot on the right are all the foregrounds just for reference in the dotted lines. I think they're kind of hard to see here, but they're there just for reference. Then you see the spectrum for the CAB, which is plotted in the solid line in orange. And then for reference, I also include the Y distortion, so the TSZ distortion in the CMB, and then our newly calculated signal in the red in the lower right corner. And we also include, for reference, the noise level for an extended PIXI mission. PIXI here stands for the Primordial Inflation Explorer, which is a proposed NASA mission. So what we found so far, we're still working on the more proper forecasting for how detectable the signal would be. But we found this new signal that should be observable in the millimeter sky, and that should be included in further analyses once you go into the longer wavelength ranges. It could also be very useful for us in the future to further understand CAB, in particular the redshift evolution of CAB, because our calculated signal is closely related to the model that we're using for these calculations. So that would be a pretty useful probe to as well understand the distribution of star-forming galaxies. Yeah, that's all. Thank you.
Thank you very much. Unfortunately, we have to move on to our final speaker, Zihui Wang. Thanks.
Okay, hi everyone. So my name is Zihui Wang, and I'm a grad student at NYU. Most of my work has to do with particle physics, but today I'm going to tell you about the most astrophysics work I have done with these brilliant collaborators. Okay, so microlensing is a very powerful technique to constrain primordial black hole dark matter. So what's happening is you have a telescope that can measure the brightness of a star on the time domain. And now there is a black hole crossing the line of sight at this time. And then around the time of crossing, the brightness of the star will be magnified. And for most of the telescopes, if the peak brightness of the light curve is at least 30% above the baseline brightness, then the telescope will identify one microlensing event has happened. And the statistical rate of microlensing will just depend on the mass of the black hole and the abundance of black holes in the dark matter halo. So that's how you can constrain the abundance of primordial black holes in dark matter halos. Now, there are actually two hidden assumptions here made by a lot of papers, but very often these two assumptions are wrong. So the first assumption is that the background star is point-like. So now let's imagine I have a large star, but a smaller length. So what's happening here is the light from the outer part of the star will just go straight to the telescope without getting lensed by the lens. And only the light from the central part of the light of the star is lensed by the lens. So the total apparent brightness of the star will be reduced. And if you still assume this star is point-like, then you will overestimate the lensing rate. And the second assumption is that the lens is also point-like. So of course, for black holes, that's a very good approximation. But if you are studying non-black hole lenses, then the size of the lens is also important. Okay, so why are we interested in large lenses? So in many dark matter models, especially in axion dark matter models, the axion particles can form gravitationally bound structures known as mini clusters or mini halos. And also in the for WIMP particles, the theoretically possible minimum mass of the subhalo can be as low as 10 to the minus 6 solar masses. So dark matter forming compact lenses is not a very exotic concept. And our goal is to recast the microlensing limits on black holes, which assume point-like lenses, to these large lenses. And in my talk, I will assume that my lens has a NFW density profile. So here is our result from the Subaru telescope. The x-axis is the mass of the NFW halo, the subhalo, and the y-axis is the upper limit on the fraction of dark matter in the form of NFW subhalo at that mass. And so this outer curve is for point-like lenses, and then we increase the spatial size of the lens from 0 to all the way up to 100 solar radii. And as you can see, the larger the lens, the weaker the constraint. Now you can imagine if you further increase the size of the lens, then eventually the telescope will completely lose sensitivity to those larger lenses. Okay, to sum up, we have shown that the present microlensing surveys can probe compact dark matter structures smaller than 1,000 solar radii. And another thing is, so in my study, I have only used one piece of information from the light curve, which is the peak brightness of the light curve. Now imagine on one day, I do see a micro lens light curve. Then how can I tell you what kind of lens is causing this microlensing event? So in order to do that, I will have to analyze the shape of the light curve. And I think to my best of my knowledge, no one has ever done this. And I think this is a fascinating topic to work and potentially have intersection with machine learning to classify this time series brightness data. Okay, thank you.